Hello, everybody. I hope everybody can hear me, and Tom can let me know if things are ready to move along. Just a quick thumbs up if things are all right in the room. Good. Awesome. Well, thank you, everybody who's joining us either in person or on the WebAssembly North America YouTube live stream. This is the February meetup, and for the first time since before the pandemic started, we are having a actual hybrid event, in-person component to everything. Thank you very much to Cortex for offering up their office space for the in-person component, and hopefully we can run this smoothly. It's our first time doing it, so we'll see how it goes. But we think we have a setup here that will let everybody, both in person and virtual, get a good experience. So we have two speakers tonight, and Matt Butcher from Fermyon will be talking about Spin and how you can use WebAssembly to write serverless functions with WebAssembly. And then Tom will be talking about writing WebAssembly bytecode from scratch, which I believe is a very interesting trick to learn. So I believe Matt is going first. If anybody wants to correct me, they can, or one of the two of them can simply step up to the podium. I see Matt walking to the podium. All right, so
what do I do now?
Here's Matt. There he is.
I walked to the podium. The magic is supposed to happen for me, right?
Yep.
I'm excited because a lot of the presentations I tend to give have been. Oh, it's on autoplay.
Shoot.
We don't. This is all preamble for. But a lot of the presentations I've given have been, very, very scripted and carefully orchestrated, and because they're pitches to VCs or their presentations to the community and stuff like that. And a lot of times it starts with sort of explaining this is what WebAssembly is and this is how it goes. So I'm really excited because tonight, giving me kind of an opportunity to talk to a bunch of people who have been taking this journey along with us at Fermyon, right? We're all part of this new ecosystem that is really gaining momentum right now. And it's a chance to kind of step into the honest zone and say, here are some of the things that we learned, and here are a couple of things we did wrong as we went, and here are some assumptions that didn't work out, along with telling kind of why we got into WebAssembly and what was attractive about it, and why I continue to be so excited. So my background is engineering. I'm the CEO of Fermyon. Prior to really getting into the WebAssembly ecosystem, I worked a lot in the Kubernetes space. Worked at Microsoft with a team that largely came over from Deis when Deis was acquired by Microsoft. And we were building a whole bunch of open source tools that were designed to fit into the container ecosystem and were designed to be part of the Kubernetes ecosystem, things like Helm and Brigade and Draft and OAM and CNAB and stuff like that. That actually, and I'll tell the story as we go, but that's actually kind of what led us into WebAssembly. And I feel like it's important to add as a disclaimer, my background still is going to come through, that this is the container ecosystem led us to the WebAssembly ecosystem. I don't get to code anymore. And while I put this on the slide sort of before doing the presentation, this is actually highly relevant because I thought that I could travel with just an iPad instead of a laptop, because if I don't need to code, then what do I need a full laptop for? And then I realized that I wanted to give a coding demonstration and I couldn't. So I recorded the whole thing and then got here and couldn't get the iPad working on the podium and couldn't email a gigantic file with a huge embedded video. So there will be no demo. I'll leave it to, I hear that Tom will read enough code for all of us. So, CEO life, I'm not good at it yet. So to give you kind of a background, I had what I think is the best job at Microsoft. Our team was basically charged with doing two things. We were in the Azure Kubernetes team, but our goal was, and our mandate was, Go out there and build interesting tools that solve real world problems for whoever's out there trying to build things with the containers and Kubernetes and things like that, and open source them. And the idea was simultaneously we could help sort of build out all of the potential for the container ecosystem and be good open source stewards and open source citizens on behalf of Microsoft. And so it was a really great job. And we would get to talk to all kinds of people. We went to KubeCons and Open Source Summit and conferences like that. I went to visit customers, Microsoft customers on site, and would sit down with them and say, I know you're starting your journey on containers. What are the big problems and what's frustrating and what's working well? And just kind of get a chance to listen and hear. And then, of course, we got to talk to other teams inside of Microsoft and hear, how Azure Compute works, what the .NET team is doing, what is HoloLens? It was really great. Getting that level of exposure turned out to be really formative because you start to encounter problems that you think very optimistically, oh, we can solve this, right? Containers, there's got to be a way to take a container and build sort of one Docker image that can run on both Windows and on Linux and on ARM and on Intel. And so we would tackle these problems and then realize how complex they were. And some of the problems we ended up solving, that one in particular, we didn't. And so we started kind of keeping track of the things that we couldn't do well. And that gave us sort of fodder for trying new things. So whenever it was time to go out and experiment, we do that. One of the things that Kubernetes really sort of opened our eyes to was the potential for distributed computing. And if you rewind maybe 10 years back and start talking about distributed computing, people would immediately assume that you were an academic and that you were talking about grad level research and something to that extent. And Brendan Burns, the guy who created Kubernetes, one of his favorite phrases as Kubernetes was sort of growing was, we need to make distributed computing into a CS 101 course. And what he meant by that was Kubernetes should make it so intuitive that we can do distributed computing and should solve the core problems to such an extent that that's the first thing you learn and not the thing that you go on to get your PhD in. And I mean, and to some extent, I think it was successful when coupled with patterns like microservices and service meshes and sort of the litany of other tooling around there. But I don't know if I don't know if I were braver, I would ask for a poll. How many think we've hit CS 101 with distributed computing? But it at least opened my eyes to the fact that we were making real progress on a problem that I had discounted as being far too theoretical to ever really warrant kind of that day-to-day work that we were doing. But it also opened my eyes to another thing, which is that we were not really accomplishing what we sort of, or at least what I sort of intuitively felt was real distributed computing. We got to the point where within a cluster inside of a data center, we could distribute workloads well, and we could set up our microservices and have them successfully communicate. But, the kind of ideal of distributed computing where we could say, here's my application, run it, in whatever way, wherever proximity allows to be the best experience that a user can have, right? Maybe that means being able to have it float down to your phone and be able to use your phone to run the application and then move back to the data center. And, there were all of these sort of like hypothetical, almost sci-fi ideas of what distributed computing could be that suddenly became really intriguing to me because we were telling people distributed computing is now CS 101. And so that, as a team, as we started talking about that, we got really intrigued about the possibilities of what if distributed computing is a staircase and Kubernetes got us up the first 3 or 4 stairs, what's left to do before we hit this kind of sci-fi future? Around the same time that we're starting to have these conversations, serverless functions really sort of took off. Right, and Lambda being sort of the easy example, but Azure Functions and Google Functions and OpenFaaS and a whole bunch of different solutions started to pop up. And, I heard 2 things from developers about serverless functions. The first one was, we really like the programming model, right? I really, instead of having to stand up a server and, manage the process and do all the threading and have 1,000 libraries, I can just write one little unit, a function, and it'll get a request, and I deal with the request, and I write a response. So I'm immediately dealing with the stuff I actually care about instead of necessarily having to do the same old kind of boilerplate thing. And over and over, I would hear developers articulate this, and in fact, that's the way I felt when I wrote them. It was like a great shot of adrenaline. I'm like, oh, hey, I was productive in 5 minutes or less. But the other thing that I heard quite frequently is it's got some frustrating points. One of them is serverless computing tends to be slow to start up. And by that, people tend to mean 200 to 500 milliseconds. So not necessarily slow on the scale of virtual machines, but slow when you're talking about trying to score 99% on a Google PageSpeed test, right? And the others where the developer experience is difficult. It can take 45 minutes to get your first Lambda function up. And then a number of sort of related ones that basically boiled down to the developer experience was a little bit rough and the performance profile wasn't quite where I wanted. But, going back to that story of distributed computing, right? Serverless functions started to look like possibly that next step on the staircase toward true distributed computing, because they're nice. If done well, we're thinking, oh, well, this would be the right unit of code to be able to sort of move around to the place that makes the most sense to run it. So serverless functions sort of became the thing that we started to focus on. So, again, this story is leading up. It's like the Titanic, right? We know from the title that the boat's going to sink at the end, but this is the journey that started really leading us toward WebAssembly. So I like to show this diagram, and I know some of you have seen this before, but this is my mental model for cloud computing, right? In the before times, we used to run one operating system on one piece of hardware, and then along come virtual machines. And suddenly a new possibility opens up here. The one-to-one relationship between a virtual machine or between an operating system and the piece of hardware sort of dissolves. And suddenly, thanks to the hypervisor, I can start running a whole bunch of virtual machines on the same piece of hardware. And that opened up the really cool part, which is I can package up my operating system and ship it off to somebody else, and they will run it for me, and I'll pay their electricity bill. And that was kind of the first step into cloud. Then along came containers a few years later. And me, in my sort of naive way of parsing the world around me, went, oh, containers, they're like a little slice of the operating system. Instead of packaging the whole thing, we only need to package a slice of it, just the file system that we care about, just the libraries that we care about, and my application. And this is the naive part, right? I'm going, oh, that's gonna just wipe out virtual machines. We won't need virtual machines anymore. And I was thinking very much in that sort of zero-sum mindset, where it's like, well, this is clearly a winning technology. It's got to defeat something else so that it can win and dethrone the other thing. It only took 15 minutes at Microsoft to go, oh, right. Turns out that there are a lot of virtual machines out there, and that as we keep deploying more and more containers, we're also deploying more and more virtual machines. There is no zero-sum game. Both technologies can win, and in fact, both technologies are winning. Now, I bring this up because that was a very crucial shift in philosophy for me, a shift in mindset for me, where I went from going, there's this kind of serial list of things where one bumps off the next, and then you add another one, and you add another one. And instead started going, okay, so what are containers good for, and what are virtual machines good for? What does the Venn diagram look like? Where do they overlap? And also, when it comes to this serverless thing, maybe we should ask some harder questions about why it has some of the characteristics it has. In particular, why does it have the performance story that it has? And is there room for another kind of cloud compute that would sit alongside containers and virtual machines that could do that kind of workload better? So again, performance is one of those big stories that we're looking at with Lambda and saying, okay, a couple hundred milliseconds is too long, half a second is way too long. How do we figure out what kind of runtime we can build that'll start up and be able to scale instantly and be able to execute, zero to first instruction as fast as possible? The current way that most of these systems work, like Azure Functions and Lambda, is they're all based on virtual machines as the underlying technology. And virtual machines tend to be very slow to start on this kind of scale that we're talking. And so there's a lot of technique done to sort of pre-warm virtual machines and drop workloads on them at the last second, and then try and clean up and fill up a queue of virtual machines so that you can kind of pipe these things through. And essentially, the realization was, okay, so the technology that's underpinning this really cool idea of serverless functions is possibly not the best technology suited for the problem. So we started saying, okay, what are the characteristics that we care about? What would be the right kind of compute engine that could actually sit underneath this kind of serverless function thing that would be far more performant, far more scalable, and still be easy enough to use that developers will sort of like it, right? Resonate with it and have a desire to build these kinds of things. So we kind of started putting together a list of the kinds of things you need to be able to do well in order to realize this kind of compute platform that you can run serverless functions on. First one is going to be cloud-grade security. And what we meant by that, and what we mean by that, is an isolation model for execution. So what is it at the core of virtual machines and containers that make it possible to run these things in a multi-tenant cloud environment? Well, it's the fact that when I deploy Pepsi's virtual machine and Coke's virtual machine, it doesn't immediately open an avenue for one or the other to do nefarious things to each other, right? So we need that kind of multi-tenant capable security sandboxing model. That was kind of the first thing that started to lead us toward WebAssembly as a technology that might be a candidate for this third class of cloud computing. Because the WebAssembly security sandbox model was built for the browser and was built with a stronger isolation model in mind, I'm told, than JavaScript even, right? You want to be able to run an executable inside of the browser that doesn't really have access to anything you don't explicitly grant it access to. It can't get to the DOM, it can't get to the network, it can't get to any of these things. And that sandboxing isolation model is really attractive when you're looking at trying to build a cloud sandbox, because you really need many of those same kinds of characteristics where you say it's only the stuff I give it access to that it's allowed to make use of. So that was the first little checkbox on our wish list checked off. And that really got us going, okay, so WebAssembly, this could be an interesting technology for us. The next one was fast startup time. Virtual machines tend to take, an average size virtual machine takes minutes to start up. You can really trim it down and get it down to sub 1 second, but then you're really limiting what you can execute inside of it. Containers, same thing. 2 dozen seconds to get it up and running. You can start trimming it down, but you're really only going to get it down to second or just sub-second range. And we're going, okay, we need something that can ideally run about an order of magnitude faster than the existing Lambda functions. So we need something around 10 to 50 milliseconds. Well, turns out WebAssembly can be started up and you can be executing much faster, particularly if you can do some optimization on the binary before you start it up. And so we got really excited at this point. We just checked 2 major checkpoints off the box. Cross-platform and cross-architecture was the next one. To have a portable function that we can move around wherever, the developer shouldn't know and shouldn't have to know anything about the host operating system or the host architecture. And the reason why is because we should be able to move it around to wherever it's the most economical and the most fruitful for us to run it. Fortunately, this has been table stakes in the web browser world for quite a while now. Gone are the days where in the web browser, the page pops up with notice saying you have to be running IE6 in order to use this feature, right? And so consequently, the design of WebAssembly automatically checked off that checkbox as well. And then the last one was the difficult one. We knew we needed to be able to move these workloads around, and we needed to be able to move them fairly quickly, which meant the binary size had to be smaller than the 6 gig you'd get for a virtual machine image or the 25 to 40 meg you would get for a container. We really wanted it to be just the size of the application plus the supporting files. That part, kind of came with WebAssembly, but the second part, how do we actually do the distribution, did not. So we did quite a bit of work very early in our WebAssembly journey, kind of saying, okay, do we have to build our own? And we started building a system called Bindle that we were using to move packages around. This system ended up working fairly well, but OCI, which is the Docker Hub, Google registry, GitHub registries, ACR, all of these run these behind the scenes to store Docker containers and images, Docker images. While originally we had looked at that and not found it to be the right fit because it was really very much architected to fit just container images. A recent change to the OCI specification called the artifact spec made it possible to store any variety of different things inside of an OCI registry. And suddenly we were going, okay, well, why are we going to build our own, right? Somebody else built and solved this problem for us. So that led us to kind of the conclusion. Again, the Titanic sank at the end. WebAssembly was the thing that filled in the last box. And that brought us to kind of the next question, which was, oh, there's another class of problem that we have to keep in mind now. In virtual machines and containers, it doesn't matter what language your application is written in. The runtime doesn't care about that. As long as your operating system can start up and get its thing going, the underlying environment doesn't care. Same with containers. But with WebAssembly, if we're just shipping around the application binary, it has to be compiled to WebAssembly. Suddenly we have to start telling the story, oh, today you can only use these 3 languages. Tomorrow, maybe you'll be up to 5, and hopefully, we'll get upwards of 10 or 15 later on, right? And that's a difficult story to tell under normal circumstances. However, in this case, the nice thing about the way that the serverless functions ecosystem had sort of developed, that was a constraint of that system already. Already there were only several first-class libraries supported on Lambda, same with Azure Functions, same with Google Functions. So in a way, we sort of lucked out on that one. But we realized that that was going to be the thing that WebAssembly had to succeed at as a whole ecosystem if any part of this ecosystem was going to flourish. It could not be a Rust only or C only or just Rust and C and JavaScript kind of community. We had to very rapidly start making progress towards supporting all of the languages. So we actually track RedMonk's top 20 languages. There are a couple on there that, like CSS is on the RedMonk top language. I don't think we're ever going to see a CSS WebAssembly compiler because it doesn't really make sense. But for about 17 of the languages out of the top 20, they really need to succeed in WebAssembly. Of those 16, at this point, only a year and some after we started this matrix, 16 of them have made progress on that to varying degrees. I think Objective-C is one of the ones that, if anybody knows anybody doing WebAssembly and Objective-C, I'd love to hear about it, because that's one language I haven't found anything about WebAssembly support for. But most of the others, including PHP and Ruby and Python and a bunch of the scripting languages now have support. So we made it kind of through this design phase and realized sort of what our Achilles heel would be as far as languages went. And we said, all right, let's build a thing. How are we going to do this? Well, WebAssembly at the core doesn't support much access to anything at all, right? It's great for calculators, but we didn't have much else that we could do. But the WASI, the WebAssembly System Interface, WASI, basically augmented this by providing POSIX primitives for your guest binary, particularly file access, environment variable access, system time, random number generator, things like that. And that was enough. We said, all right, if we've got this, right, if we can only rely on those kinds of things, how do we build a serverless platform? Notably absent in the list I just gave you was networking, right? And networking is generally one of the things we think that serverless should be fairly good at. So we took an interesting stab at the problem by going back to the 90s and saying, okay, how did the web get started and what were the ways that people originally did these kinds of, dynamic web pages they were called at the time, right? Well, CGI. And the idea in CGI was your web server gets a request that comes in and it says, oh, that maps to some program on the system. I'm going to execute that program and pipe in all of the requests, all of the pieces of the HTTP request in the form of environment variables and files. And then whatever it writes standard out, I'll just send back to the web browser. And we went, well, that matches up feature-wise with WASI. And so our first stab at building this was really a CGI implementation. We called it WAGI for WebAssembly Gateway Interface, and it essentially piped everything into the execution context for WebAssembly in the form of environment variables and files that were injected at the WASI layer. Kind of cool, worked okay. We actually built a couple of things on this model that worked reasonably well, but it wasn't enough. We very quickly realized that if we wanted to build more sophisticated applications, we were going to need things like outbound HTTP, key value storage, database access, and all the normal things we use under the name full stack, right? We need a whole bunch of stuff in order to build today's modern web application, and most of those things were not part of the WASI Preview 1. Right? So that got us kind of rethinking the way we built things, and that's where Spin came from. Spin was our attempt to build a developer toolkit that focused more on being a serverless function development tool than it did on doing what WebAssembly could do today. And so we built this tool that you could type spin new and your favorite language, and it would spit out the template you needed, which was just the function and the right imports. And then you go away and then you do spin build, and it calls out the right command for your particular language of choice and builds the WebAssembly binary, and then you type spin deploy and it pushes it up somewhere to run it. Okay. That came with a couple of challenges because it's very deeply important to us to be good members of the broader WebAssembly ecosystem. And to us, kind of the next big steps in the WebAssembly ecosystem will be the continued development of WASI, but also the component model. And the component model will really provide us a way to sort of assemble an environment out of pre-existing WebAssembly binaries and wire them all up together. We knew that as we built these things, we wanted to build spins so that it kind of previewed what the component environment would be like. And then as the component model began to mature, we could sort of underneath the hood swap in the component model and swap out our sort of unique way of doing things. And so that has been one of our challenges that has been an ongoing thing that we've been doing as we build spin. So we built an environment to create serverless functions. The first one, Waggy, was not quite what we wanted it to be. Incidentally, we still do have Waggy support in spin. We built the CGI version, not quite what we wanted, built spin. We were much happier with it. And then we got to this point where we said, all right, now we need to give developers a way to run these kinds of applications. And this is where we made kind of a funny misstep that's a little embarrassing to talk about it in hindsight. We had the kind of goggles on where you see the problem immediately ahead of you and you start talking yourself into a solution and then get convinced that this solution is the right next step. And then somebody else has to intervene and say, that's not the right next step. So what we thought we were going to build was what we called the Fermyon playground. And the idea was you write your application locally and you're in your kind of inner development loop, right? And you're typing away and you're building, and then you want to test it. And the idea was you'd type in spin play and it would push your WebAssembly module up into a Fermyon operated cloud, and you'd get 5 to 15 minutes where you could just kind of test it out there. And then after we never did decide on an amount of time, but 15 minutes we'll go with. And after 15 minutes expires, then your application gets deleted out of the cloud and you can just keep going. And the next time you're ready to test, you can do spin play and it'll create a new one up there and you can show your friends and colleagues, oh, look what I did. I don't know, in hindsight, even as I articulate it now, I'm like, I really legitimately thought that was going to be the right move. So we started building this system, and then we started floating it by, our friends and other developers and saying, it's great. When you're in that inner loop, you can type spin play, and it'll start up this playground, and it'll be around for 5 minutes or maybe 15 minutes. If maybe we could even go as high as an hour. And they're going, why are you deleting my app? Well, because then it'll make it really easy for you to stay, in flow as you're writing your code. And I had told myself a very elaborate story about why this was a good idea. And over, the first 4 or 5 people we pitched this to said, it's an interesting idea, but why are you deleting the app? You don't need to delete the app, do you? Yeah. Can you just explain why would you delete my app? Could I just have it up there all the time? Well, you're in your inner loop of, no, I just want to know. And so we're coming up on KubeCon, and we had planned on debuting spin play at KubeCon last year in Detroit. And it's like September, and KubeCon's in October. And all of a sudden, we kind of go, oh, right, we actually shouldn't delete the app. Everybody is right. But that means that between now and October, we kind of have to build a cloud, like something where people can run things and keep them running for a long period of time. So we pulled one of those ridiculous startup-y pivots where you're like, hey, everybody, new idea. Okay, we're going to do this. And you got, 2.5 weeks to do it. And everybody started, kind of plowing through the code. And in October, we released Fermyon Cloud, which was essentially Playground without any time boxing on it. So, this is kind of the journey we've taken to this point. So Fermyon Cloud being kind of the last thing we released, which is essentially a deployment target where you can type spin deploy and it'll push your WebAssembly serverless app up there and you can test it out and play around with it. We got to that point, essentially December of last year. And we kind of looked at it and said, this feels like the end of chapter 1. We set out to say, we're going to, we've got this big problem that eventually we as an entire ecosystem want to solve, right? That's this distributed computing story where we go from stair number 3 with Kubernetes up to stair number whatever it is. And stair number 4 is just getting this serverless function thing nailed in kind of a new way. and introducing a third kind of cloud computing environment that's going to work really well for these workloads that we have to be able to port around and move around. And we went from that into, investigating languages, building our first Waggy thing, moving on to Spin, and then really, at the end of last year, releasing this Fermyon cloud platform. And now we're looking at it going, all right, so what's next? Well, next we start on the full stack stuff and then begin doing databases and things like that. But it has been a really interesting journey for us and kind of a fun way of, even now looking back and getting this opportunity to kind of share with a bunch of people who have already taken, a similar journey in seeing WebAssembly and saying, what can WebAssembly kind of offer? What are its value? What's its value to me? How do I apply those values? That's kind of the journey we've walked so far. And it's fun to look back and say, I mean, yeah, we stumbled our way into this thing, but the community and the ecosystem around WebAssembly is really gaining momentum now, and it's very exciting to see where we're going. With that, if you want to, come hang out with us on Discord, I left a link there, or you can follow us on Twitter. If you want to try out Fermyon, you can just go to fermyon.com, download Spin, play around with it, and I would have shown you a demo, except I deleted it out of my deck. So, how are we on time?
I think we're all right. If Connor,
Hello.
Connor, yeah, if you see what you want to do, we could do questions now or whatever you were thinking.
Yep. If anybody on the live stream wants to send in questions, they can put them in the YouTube chat or the Discord Wasm NA channel. And if anybody in the audience wants to ask questions, they could just talk to Matt because he's standing right there.
One of my colleagues, Chris, threatened today that he was going to use ChatGPT to ask it, what are questions that Matt can't answer?
Oh.
There are a lot of them, I'm sure. I mean,
I'll see if I can log into the OpenAI account fast enough to make that happen.
The goal was not a challenge there.
All right. We'll give folks a couple of seconds to put in their questions. Otherwise, we'll get ready for Tom.
Yep. I got a question. So the question was, how do I think about WebAssembly in the context of the browser? And I can even expand that and say, other places where WebAssembly fits. Sort of my view is there are at least 4 fairly big categories where WebAssembly can shine, right? And I feel like everything I've talked to, 4 fairly large categories, and I've talked about sort of like our little bullet hole over here in the cloud world. And the 4 categories, browser is the first, right? It was built for the browser. We've already seen Figma, make very good use of WebAssembly and prove that as a startup, they can become highly financially viable by using WebAssembly to do some really serious number crunching. And I think that the browser game, interestingly, I don't think has come anywhere near fulfilling its potential. I think we're all just starting to understand the different ways that we can build applications in the browser. Blazor from Microsoft was a good example of a first take at a framework, and then we're starting to see them kind of all over. I'm really excited to see how all of these things will play out. It's not my area of specialty, so I have nothing to contribute as far as prognostications or predictions, but I think we're just now starting to see the momentum where it needs to be to see kind of a new generation of browser technology built on it. Second area, I think, is plugins, right? I think a friend of mine calls WebAssembly the last plugin model we'll ever need, because if we do it well, then any language should be usable on the guest side, right? And it just becomes a matter of embedding these kinds of a hosting environment in the right place and exposing the right APIs. I think that's really exciting. I think we're seeing it everywhere from, potentially an answer to the long-lived webhook idea, where instead of, calling out to something, you can run it. In fact, that's Connor's the inspiration behind this idea. But also in places like user-defined functions and databases, the way a single store is doing it. IoT and Edge are another good, far Edge are, I think, another good case, because the WebAssembly binary format is versatile enough that you can run it in very low memory, very low powered environments. And this is one of the things that's exciting about the distributed computing story writ large, right? If you can run it in a really small, really constrained environment, and you can run it in a gigantic server environment and not have to make changes to your binary, that's a huge win when your ultimate goal is distributed computing. And the last one is cloud and far edge, right? The stuff that we're doing, which I think there's a ton of potential even well beyond the kind of serverless functions that we at Fermyon are focused on.
You guys had posted videos a couple weeks back. You talked about language support and just some of the things that you kind of learned about it. And even just kind of hearing today, like, you know, even with like serverless, like you were going to do, it was that experience of like really kind of, I mean, we're seeing traction now like years later, but Thomas was like, one month back.
Yeah.
Do you feel like now, like, this is like really the focus this year, like with Fermyon, like to get things production ready, to get things in the library, like, because that's why I feel like there's this trough, like,
yeah,
like I've been like waiting, and I'm like, I don't know if we're gonna get there this year. Like, what is your observation where we're at? All
right, I'm going to try and paraphrase it in short form for the microphone.
Sure.
So the question is really, are we starting to see, particularly at the end of last year and for this year, the move of WebAssembly sort of as an ecosystem toward production ready, and you know, maybe more specifically, does Fermyon think Fermyon is heading toward production ready by the end of 2023? And the answer to that is yes. If I were Connor, I would have just said yep, and then left it. but the slightly richer story is that we knew language support had to be that it's absolutely critical, right? We knew that for WebAssembly to reach its full potential, we had to have a broad array of languages, and not just compiled languages and not just systems languages, but scripting languages and hybrid languages like Java and the .NET framework. And we're seeing that happen. We needed to see the specifications for WASI really start to make some progress and solidify. WASI Preview 2 is coming out shortly, so we're seeing a major upgrade to WASI after about a year and a half. And that is a huge indicator. The component model is the next one, and it also is coming along very quickly now. I would love to throw out times when I think that will be done. I'm going to say next Tuesday, but it's probably not going to happen quite that fast. But that one's a really major piece of the bigger, again, the sort of WebAssembly writ large story, where we can take different binaries and join them together at the host runtime level and do some really interesting things there. So yeah, I think that 2023, by the end of 2023, we will see a pretty good amount of the WebAssembly ecosystem, you know, in scare quotes, really production ready. And Fermyon's goal, in fact, for 2023 is to not be production ready, but to have things running in production and demonstrate how robust and reliable a WebAssembly-based cloud environment can be.
We have a question from the live stream audience. You said you're using Wasm for sandboxing. Are you adding anything on top of your Wasm runtime to isolate the code, or are you purely relying on the WebAssembly security model?
Every time you say anything, Connor, it's like the voice of the divine coming from behind me. I kind of jump. yes, whatever you say. I was going to repeat that question, but I also don't have to repeat that question. For the most part, when it comes to the execution of code, the one piece of security that we have had to be very cognizant of is how to fulfill the contracts of WASI, right? So WASI says, as guest code, you can open a file and you can read environment variables and you can access the system clock and things like that. And when you're writing your code that you compile to a WASI compatible binary, that's the way it should feel to you, right? You just use the regular old ways to open a file. But when it comes to the security boundary around that, it's up to the implementer to say, okay, this is how I'm going to fulfill that contract. So we do a lot by storing data in memory and presenting it as if it were a file system, and storing environment variables in memory and presenting them as if they were part of an environment, right? There's no rocket science behind that. Cloud has been doing this for a long time, but you do have to be very careful, because if you do it incorrectly, you're building a porous layer on top of something that was supposed to be secure. So we get kind of antsy when it's like, well, how are we going to hook this up to a database? Well, we better make sure that we're not wiring up something that will allow somebody to escape from the WebAssembly sandbox when they're connecting to a database or something like that. And that, I think, is kind of the main security challenge for us. There are other things, but they escape me at this moment what they might have been. That's kind of the one that's been the focus of our attention.
Awesome. And another question, open source vulnerabilities are a major concern for many organizations, and traditional approaches to software security, such as vulnerability scanning and patching, can be resource intensive and prone to errors. How can WebAssembly, with its ability to isolate code and provide a secure execution environment, help mitigate the risks associated with open source vulnerabilities? And what are the challenges of implementing such a solution?
So I heard the question as, tell us more about Fermyon, and completely ignore the really hard question. No, security is, we can really talk about two facets of this question, right? One is that as a human endeavor, it is somewhat, all of coding is somewhat prone to errors, some of which become security holes. And it behooves us all to build environments that help resist that kind of thing. And I think WebAssembly's sandboxing model is a great first step toward being able to do that. And if you can control the amount of memory used and the amount of CPU used, you can also control, at least deal with a class of errors that happen when something goes into runaway mode and is consuming vast amounts of CPU or vast amounts of memory. I'm going to flip that to the more dangerous bit there and say a lot of work is being done in my answer by the assumption that WebAssembly itself is doing security well, right? And by extension, I just talked about how Fermyon has built our own, implementations of some of the WASI underpinnings. We've got a litany of different runtimes out there, each of which has implemented these details in slightly different ways. And so we all have to kind of be honest and say, we believe we are building a very secure system. We are still amassing evidence to prove that we are building a very secure system. A lot of the security research that's happened recently has shown, flaws that can happen inside of the runtime. We haven't seen any breakouts from the guest code into the host mode, into the host operating system or the host environment. And that's really good, right? That's the real danger we're trying to control for in WebAssembly. An analogy to this, drawing from the container world, is, containers don't do anything to stop bad code inside the container from being bad code. Its job is to isolate the container so that when bad code happens, it can't get out of the container and into the host operating system. This is where I'm going to maybe get preachy and say it is really important for us to be honest in all of open source in saying, look, there was a vulnerability here. Here's what the vulnerability was. Here's how we fixed it, right? So I really like the fact that what we have seen is when Wasm time has a vulnerability, they report it. When security researchers release something saying, here's a problem, the community doesn't say, oh, no, pay no attention to the man behind the curtain, right? They say, okay, well, what do we need to do in order to fix it? How do we mitigate it? Let's talk about that. That security story is going to be absolutely critical for us to nail, regardless of which of those four domains we're talking about, right? Critical for the browser, critical for the plugin model, critical for the server and cloud model, and critical for the IoT model. So it is, I think a lot of people are doing a lot of work here, and it's so far has been proven to be a fairly robust system, but we have to go into it with our eyes wide open and say, we're entering a critical time as an ecosystem where if there are big vulnerabilities in there, we have a lot more eyeballs looking for them at this point.
Awesome. And you answered that question perfectly, and I'll have you know it was, in fact, from ChatGPT. So good job.
Oh my gosh. There we go. Don't trust ChatGPT. It's wrong. I thought it was going to ask me a question about flour varietals or how to cook bacon, things that I cannot do. So
I did specifically ask it for a question that would stump you, and it said, as an AI language model, I cannot predict with certainty what would stump Matt Butcher, CEO of Fermyon, but here's a question that may be challenging. So I think you did pretty well.
Oh,
all right.
Chris, I'm blaming you for that one then.
All right. If there's any other questions in the room, we can do those, and then we can move on.
Yeah.
So I'm curious, how would you contrast, just building on your answer to the ChatGPT question, how would you contrast the Bytecode Alliance approach and sort of the general WebAssembly approach to the unknown unknowns versus
yeah.
Well, in fact, the ChatGPT sort of approach, the large language model approach to where oh, okay, well, we're going to throw this out into the universe, and maybe it's going to screw everything up, and maybe it won't, and we'll find out.
Okay. My background is not computer science. It is philosophy. So I love questions like that.
You can repeat the string, please.
So in the next 2.5 hours, I'm going, no. We have created a technology in ChatGPT that we have, for some reason, automatically attached an assumption that it has to be more accurate than any beta level technology is ever going to be, right? And part of that is because we earnestly pursue this kind of idea, talking about staircases toward an idea, a big idea, right? An idea toward artificial intelligence. And so consequently, people are rather intolerant of mistakes made by a fairly beta technology. Yet at the same time, we like to turn a blind eye to the fact that most of the technologies we're running in production are not actually, flawless technologies. And we write that off as, oh yeah, there's bugs in any system. So I think on one hand, we're attaching too high of a standard to some of these technologies, and on the other, this is going to come back to bite me someday. Someday somebody's going to be like, well, Matt said. But yeah, in some ways, I think we're attaching too much importance to a beta grade product that is not yet where it's gonna be, right? It has not yet gotten good enough. And perhaps the reason why is because the profoundness of the impact, if it turns out to be a nefarious or evil technology, might be beyond anything we assumed. WebAssembly probably doesn't have the nefarious potential that ChatGPT does. But on the other hand, we have to be somewhat tolerant and say, yeah, it's an early technology. With WebAssembly, we really do want to take the opposite, push it the opposite direction and say, okay, if we're going to use this as an isolation model that's supposed to underpin all these different kinds of environments, we really do need to be, almost brutal in the testing, right? And say we really need to be certain that the sandbox is as good as it is. And when we write extensions to this, we need to make sure that the extensions, which are the point where we could introduce a weakness, that we really do our diligence on those as well. Did that get to the, okay, all right. How are we doing, Connor?
Pretty good. I think we can get Tom up here and move.
All right.
On
Sounds great. Thank you very much.
Thank you very much, Matt. So next up, we're going to have Tom, who's a software developer at Convex, and he's going to be talking us through how to write Wasm bytecode. So I will hand it off to him.
Great. I've got a screen share up, Connor. Is that? So I want to make you're going to disappear from me here. I'm going to pull up one of these terminal things.
You are good to go.
Cool. Cool. So I'm Tom. I work at Convex, and we're happy to be hosting tonight. It's exciting to have everybody here. We are a backend as a service where, of course, we're thinking a lot about WebAssembly because that is a way that we could be running these backend functions. But right now, our backend functions run in JavaScript. I've been excited about WebAssembly for a long time. I mean, relative, or not as long as folks that have been thinking about it for this long, but as long as it has been a thing, it's like, wow, I can do this in a browser. This is so cool. I didn't quite hear all of Matt's talk because I had some work stuff, so I wasn't quite paying attention. But I heard a few pieces in there about language support or these other programming languages, and that kind of confused me because to me, WebAssembly is a way you can write some bytes and then the code runs, right? We call it WebAssembly because assembly code is this thing, right? We've got, maybe you'd write the stuff on the right, but that's kind of just a learning tool. Really, it's about this stuff on the left. And so that's what I want to talk about. Let's just get right to it. None of this, theoretical language support stuff people are talking about. Let's just write the WebAssembly. So when you write WebAssembly, right, we can do this in browsers, we can do it in Node, we can do it in a lot of environments, I hear, but those are the ones I'm familiar with. So let's write I'm going to call it program. Probably have some of those already. program4.mjs. And the way that you write WebAssembly is I guess you start with a array of byte-like things. And we're going to need to turn it into a real array of bytes. That's going to look like, we'll call it bytes, can be a new uint 8 array for that code. Then you need to create a WebAssembly module. Say module equals WebAssembly.compile. So We're going to compile those bytes. And then you need to instantiate that module. Let's we call it instance. It's the WebAssembly instantiate, yeah. Instantiate that module, great. Oh, I'm running over my line limit. And then instance is this thing that has an exports property on it, and that exports property is going to have some functions on it. And those are the functions that we are going to write in WebAssembly. And this is the overall WebAssembly thing. The goal is just to get something I can use from JavaScript or from other host languages. Ideas for what to call our function, we can come back to it. But we're going to write something here, and that's going to be a function. And we can console.log the result of calling that function. So the whole point of all this is to build this thing here. So the way WebAssembly works is we start off with a magic number. We have several bytes that identify this thing as WebAssembly. Those numbers are, it's a 0, and then it's an A, and then an S, and an M for assembly. But that's not going to work. I need the byte value of this. I could say a.carcode at, that's a way in JavaScript to get that thing, but that looks kind of gross. So let's just find out what that is. a.carcode at 97, great. So let's go all the way here. 97, 115, it so happens, if you know your ASCII, and 109, I think. And the next thing we do is a version number. Anyone know what version of WebAssembly we're on right now? Any got a guess? It's a single-digit number.
2.
Good guess. It's 1. This is a little endian 4-byte 1, I think. So it's 1000. Cool. Now the way WebAssembly binary format works is there's this great guide. It's kind of new to have it look so nice. There are these. Let's see. There are these different sections that belong in the WebAssembly binary, and we're going to need a few of them. Each section looks better. Great, we're safe. 4 different sections we're going to need. First section is, looking at my thing here, great, we're going to need a type section. The second byte in each section is the length of that section. And if you only have 1 byte to describe a number, that means you don't have that many numbers you can describe. But fortunately, we're using this variable length encoding called, what is it? Little endian base 128. It's just like Unicode, where you say, gosh, I wish I could represent characters of different sizes and different numbers of bytes. And we would have to learn it. It's pretty neat. It's kind of an academic, fun CSE thing where you say, let's take the first 7 bits and use those to describe a number, and then have a continuation bit that says whether this is going to be the last one or not. But if we just restrict ourselves to numbers less than 128, we don't have to worry about that. So we're going to do that. I don't need numbers bigger than 128 most of my program anyway. So this is where we need to say the length of that section. I don't know yet because I haven't written it yet. Okay, and this is where probably have to cheat a little bit, because this function section is where we say, oh no, type section. The type section, yep, I'm already going to cheat. Sorry, I'm going to close some tabs so I can cheat faster. Convex is great. You can see me doing the convex stuff here. Here we go. The way I want to cheat is that I wrote down some of my special numbers. Where are they? Right. Here we go. These are my magic numbers I always forget. And also here's the program we're trying to write, and maybe I'll cheat a little bit. The type section, okay. Right. Oh, we're writing from scratch. All right, we're back over here. The type section is where we say, these are the types of the different functions we're going to define in here. You can define some other types too. The type that we need to describe is, we have one the third byte of the type section is how many types we're going to describe. We only have one type that we're describing here. The next thing is this 0x60 is saying I want to describe the type of a function. So I say 0x60. The type of this function takes 0 arguments. So I put a 0. This has 1 return value. The WebAssembly binary format lets you have multiple return values. So I just need 1 here. And gosh, what is this one? I don't know what this magic byte is. So it's good I'm cheating. The next section we need, let's have comments. This is the types section. Next we have the function section, I think. Yep, that's right. Function section is easy to remember. 3 is the name of the section. 2 is for how many bytes are in the section. Oh, we finished this. 1, 2, 3, 4, 5 bytes. So I'll put a 5 here. Great. The function section, we're going to say there's one function that I want to declare in this code, and it will use the type in the index into the types array it needs is 0. Halfway there, our third section in here is going to be all left my head now. So oh, an export section. So now we need to describe what we're going to expose to the outside world. This is section export. Section 7 is well, we don't know what the length of the section will be yet. We're going to have one export, and we have to know the length. So what should our function name be? Please make it short. Something you know the ASCII codes for. Something like ABC. I heard ABC. I'm going to do ABC. I think that's 90 something. Oh, I'm going to forget it. Yeah, 97. So I need to know the length of that export. 3. 97, 98, 99. Great. And then I say that this thing I am exporting is a function. I think is how this works, right? Yep. It is a function, which is 0, and it is at index 0 in my function section. So I put a 0. Great. And last section. This is the tricky one though. And it's time to actually write some code. This is the code section. Oh, that'll count up our bytes. 1, 2, 3, 4, 5, 6, 7. Great. Okay, here goes. So this is the section number for the code is 10, but the cool way to write 10 is to say, what is it? 0A, much cooler. And okay, all left. All right, oh, we got our answers right here. Okay, that's reassuring. This is the length of that section. I don't know how long it's going to be yet. I'm going to define one piece of code in this section. I don't know what the length of that code will be yet either. We'll have to do some algebra to figure out what these numbers are going to be. And now I am writing a function. And first I have to say, how many local variables will I need in this function? Now I've already composed the function in my head because that's what we all have to do in WebAssembly. We don't have language support. We have to just know. So I'm going to say, let's write a function that adds or multiplies or divides or whatever 2 numbers. I'm just going to hard code the numbers. I really want to know something about the numbers 7 and 14, let's say. So the first thing I need to do is push. So WebAssembly, the binary format is a stack-based machine. When I say hear this, I think, oh yeah, like the Python bytecode. This is I'm going to push stuff onto the stack. The first thing I want to push on is the constant 0. I think it's 41 maybe, and we'll cheat and find out. Yep, 41 means the next byte is described a number. And again, we're using only small numbers, so I know it'll just be a single byte. I don't have to figure out the encoding for it. Let's add, I said let's add the number 7. Now I'm going to push another thing onto the stack, 0x41. I wanted to add that to 14. And now I need the opcode for adding these 2 numbers, 0x, something like, it's hard. My autocompletion here is only for things I've already typed, so I know it's none of those. Interestingly, it's the same as a lowercase a, but I really want to write it in hex. I want to know lowercase a in hex. If 97 in hex, one way to find this out would be 97 to string in base 16. 61. Cool. So 0x61. Oh, I don't think that's right. I think it's like 6a or something. Probably the lowercase. I bet it's right, time to cheat. Yeah, 0x6a. That's what it was. Turns out that's add for adding 32-bit integers. Subtract is 0x6b. Multiply is c. Divide is d and e for the two kinds. But we're just going to add these two numbers. And that's it. I need a special byte to say the end of this code section. That's 0x, feels like, better check that one too. 0x7b. Great. And I think we're done. We've written our code. I need to count up these bytes. 1, 2, 3, 4, 5, 6. This function is 6 bytes long, which would make the whole thing 8 bytes, I think. And now we see if this works. What was this again? Program 3 or something? 4, thank you. Great. Mob programming is effective. Great. We have, okay, our error here that it's not called ASDF, ASDF. That's because it's 97, 98, 99, ABC. Okay, now we have real good errors. Can't read, oh, this says it's still not there. So maybe this is encoded wrong. ABC, 97, 98, 99, right? Now I'm popping back and forth between a working one. They see, oh, okay, well, any ideas? Missing what? Too many on what? Oh. Yeah, well, I think that's actually more correct because if it's missing the comma, it wouldn't work. Okay, let's compare this to one that actually works. Program 2. There are tools for diffing two things, but it just doesn't feel like I'm doing it from scratch. No tools. Come on, yeah. All right, so there's one issue here where 7b, I'll just bring it over. 10, 7 plus 9. Ooh, these numbers are different. That's suspicious. So maybe I counted wrong. 1, 2, 3, 4, 5, 6. Looks right to me. Where did someone see the 0?
There's a 0 between the function length and the 0x.
Oh, what does that one mean? I think that's for, gosh, I don't know what that one's for. Maybe that is saying also the index. I think that's the index into the function array, like the function section. Well, we'll find out. And now this would need to be 7, and this would need to be 7. Isn't this exciting? This is the reality of WebAssembly, right? Where it's pretty neat that you could just get to type these, but it's really only for hardcore programmers like me here. I've got different numbers I'm adding. That's fine with me. Oh, with 7b, not 0b. So my end byte was wrong. I don't know what the compiler thing you're talking about is. Change the wrong. What's that?
Too many bugs.
Oh, I'm supposed to change my one to that one. Okay, thanks. I appreciate the support here. We're going to get this to run. You're stuck here. Yeah, we're doing this. Really making these look the same. I could just copy that one in. I'm adding some different numbers. That's fine. Okay, it's time to give up and just copy in the version that probably already works. Oh, interesting. Yeah, okay. Yeah, let's console.log instance.exports. We think that's a thing. Undefined. Okay, great. Oh, look, you know what it was the whole time. I gotta await these things. We did it! Hooray! Great. Okay, so we've written the code. So it turns out WebAssembly is easy, but JavaScript is still hard, and that is an issue. Okay, but it would be really neat, right? If there were some way to or let me show you some of the tools we have here. We can, for instance, and what's the name of this one? It was program 4, great. Next thing I want to do is write out these bytes to a file, because normally the way we deal with WebAssembly code is in a .wasm file. So let's write that out. Import fs from fs, fs.write file sync, and call it code.wasm. The thing we're sticking in there is bytes. And now I'm going to run node program MJS, program 4, was it? Also, I'm going to watch program 4. I'm going to run 2 different tools on it. One of them is Wasm decompile, which is going to give us a fun representation of this code. So it's neat. It would be cool if there were these compiler things that you're all talking about. But what we do have are disassemblers. We can look at bytecode and understand it by raising it up a level and show what would happen if you parse it all out. And I'm writing to.
I wish you were in my college class.
Because I'd be getting the low ones. Yeah, I'd be helping you on the curve. Yeah, I know. All right, so hopefully we're looking at, yeah, great. Now I'm adding 4, so I screwed up. Now I'm adding 4 and 6 because I copied this out. But we wanted to add 14 and 7, was it? So this is kind of fun. So here's 2 different ways we can look at this program. This one is called the, what was it? It's a very fancy, the decompile. So normally you would like what disassembler, and that would be this stuff down here. This doesn't look like assembly code if you're used to like x86 or something, but it really is. It's just S expressions assembly code. So this is the WAT, the WebAssembly text format, looks like this. And then this is just pointing out how many fewer, like, look, this is almost TypeScript, and this is how this thing really, this would be the compact way to represent this code that we just wrote. Gosh, did I have any morals? Well, basically, this is pretty neat, and it would be real cool if there were some way to write this kind of stuff. It's kind of like TypeScript. Is anyone excited about TypeScript here? It's this neat. I'm on board intellectually. Like, it is cool that this thing checks these types for me. But then when I want to run the code and I have to go through and delete all of the type things that says colon string, and I have to go delete that, and there's colon number, and I have to go delete that just to run it. Like, it would be cool if there were tools that would automatically that word compile. If it could like turn it into a thing that did run, that would be a world of, this stuff could be really powerful. So a project I've worked on, another thing I've done with WebAssembly is, let's see, Wasm of, what was it? Advent of Wasm. So a while ago, I tried to write some WebAssembly for Advent of code, right? These simple coding problems. That was kind of fun. You can write, I even annotated it to be really good, just to show how this code works. And then I started a bigger project with WebAssembly, which was this play endless web. So there's this open source game. Shoot, sorry, that might be really loud. No, there's no audio in, it's fine. This open source C++ space game where you're running around and you're this little pilot, right? And you're ship real quick. Yeah, buy it. It's great. Nope. Now let's leave and let's fly around. This is I'm flying around. If I had a better ship, I could fire up some missiles or something. Cool stuff, right? But if we look at how this works, this is a lot of work because there aren't these compiler things you're talking about. We had to take this C++ open source game and translate it by hand into WebAssembly. It was a bunch of work. But it was pretty cool that you can do this in a browser now. You take this C++ code and it was a lot of work. Here, let me show you what some of the code looks like in here. Let's find some. I guess we could find it in here. Well. So I think when we load it in here, it'll show up. I'm looking for a Wasm file here. cd.wasm. Bottom one. Thank you. Here we go. Cool. So a fun thing that even browsers will do, right, is when I open this up, it has done that same step that we were looking at in here, where it has taken my code, which is just binary bytes, right, and it has transformed it into this form here, which is kind of nice. So I can debug it. It's a lot of work. There's a lot of it, as you can see, right? Like this is a big project. I worked so hard on this to do all this work. Anyway, but my moral here is the promise of WebAssembly is that you can get this stuff into the browser, but it's a bunch of work. Gosh, it sure would be neat if it were possible to just take existing code and just shove it into the browser. We're not there yet. All you can do is just type these things out by hand. But the promise of this, of being able to run pretty arbitrary stuff in here is pretty cool, and I've had a lot of fun with it. I think that's it. But I might go on some tangents if people can ask some questions. That's it.
Thanks, Tom. We can start off if anybody in the audience has questions.
Is this what coding interviews are like at Convex?
Right, yeah. Well, we write all our code, and we want it to be very portable, very secure, as you're talking about. And so, you need to write code from scratch. On a whiteboard, though, right? We wouldn't make you do it on a computer, yeah. Right. Unlike this, yeah. Right. No. Right. Somebody failed the other day because it was lowercase ASCII, but they were doing the uppercase. Oh, yeah, it's rough. Only the best. But I can also drop the charade. Yeah, I'm excited about WebAssembly because of these different, I'm coming from it more from this browser side. The infrastructure part's real exciting. Of yes, I'll be able to run, right now at Convex, we run V8 isolates, similar to Dino, where great, we have a way to run this lightweight code. We can do it in this custom runtime. It's very cool because we have deterministic execution that you wouldn't have in a normal JavaScript runtime. But all the time we say okay, this is great, and this is the developer experience people want now, we think, but gosh, people would like to be able to write in other languages. So this WebAssembly, as infrastructure thing is pretty exciting for that. Where I have mostly used it so far is in the browser. If I want some code, I can now say I want the Stockfish chess engine, and someone has written this thing, and I'm assuming C++, because it sounds very like a serious thing, and we can compile it and just run it in the browser. And that is, that's the immediate power, right? That was some of the first reasons to get it, like Emscripten, the big first project. Yeah, the big first project where it's look, we can take existing code and get it into the browser. The browser, it's not the only thing, but it's almost, it's the thing at least. It's not the only thing, but it's a thing that matters. And it's very exciting to be able to move these workloads in.
Cool. Well, I have a ChatGPT segment for you, but it's a slightly different one. I told ChatGPT a little bit about your talk, and I asked it to answer a question as you, and we're going to see if you agree with your answer.
Great.
So the question was, hi, Tom, I have a question for you. What, if any, practical uses could there be to writing WebAssembly bytecode by hand? And Tom, you said, that's an interesting question. Well, there are a few potential use cases where writing WebAssembly bytecode by hand could be useful. If you're working on a project that requires a lot of optimization and fine-tuning, writing WebAssembly bytecode by hand could potentially help you achieve better
If I could interrupt for a
performance.
second, yeah, agree 100% with this first one. We all know that these mythical compiler things, even if they existed, there's no way they could generate code anywhere near what a trained engineer can do by hand, right? We've known this for eons since that Fortran compiler that Ada was trying to do. Like that's ridiculous. Like we have to be writing our assembly by hand. Okay, go ahead. I'm with you so far, Connor.
And secondly, writing WebAssembly bytecode by hand could be useful if you're working on a project that needs to be lightweight and portable. Because WebAssembly is designed to be compact and efficient, writing directly in bytecode could allow you to create programs that are more compact and efficient.
Great, compact and efficient, right? Again, that's the only way to do it. None of this. Okay. Thank you. I'm glad I was a support.
And the closing paragraph, that being said, writing WebAssembly bytecode by hand is generally not recommended unless you have a very specific reason to do so. For most use cases, using a higher level language and relying on a compiler, to generate the bytecode for you is more practical and efficient.
Okay, I was with it for the first two. Great.
All right, so that's virtual Tom as trained by an AI, but does real Tom have any final things he'd like to say?
Yeah, any other, again, it's really, I'll sort of answer a question if I know, but probably I'll just talk more. But yeah, are there other questions, thoughts? The other exciting thing, I mean, my answer to that question that really, truly would be out of character, would be, I want people to understand how concrete this thing is and how available it is. In the same way that if I was teaching someone to program, like just learning programming, it would be important to me that they did it in JavaScript, because that's the browser is a thing that is there all day, every day. That is how you interact with the things. If you're just as a normal person online, like that's, you immediately see the application. And WebAssembly, similarly, yeah, you should be compiling this stuff, but it's not such a, hopefully if you can see this written out here, you can also imagine that this was a fetch and I was grabbing this code from somewhere else, and it's really not that hard to integrate WebAssembly into your existing applications today, right? It's the reason we need all this outside, these important tools that Smith is doing, the reason we need all these, and WASI and these other pieces, are that you're trying to deal with higher level things. But if you're okay with putting in integers and getting out integers, you can just do it. And even if you're okay with designating regions, this starts to sound a little silly, because no, you should be doing this, like, you should be using the code that Rust will generate for you to deal with, okay, there's this array in this shared thing where these bytes have these meanings and help us deal with the types on both sides. But I think it's exciting that it's all doable. It's all, it's very at-hand technology. You can play around with this today. And you can even bundle up individual functions and stick them in NPM modules and have a NPM install this functionality and have it work. Of course, you probably want to compile that thing. But the other important thing is this interface is, it's not bad, right? You get the code. There are better versions of these things you should be using in a web browser. There's WebAssembly.compile streaming, which lets you be loading the WAT file at the same, the Wasm file at the same time that you're compiling it. It's a streaming compilation thing. And you should be using these other versions, but it is a pretty simple interface to just get the file somehow. And that's how we're doing things like this. It is just like, yeah, I guess I'll just serve this Wasm file on S3. For this project, it was just a bunch of linker stuff I had to learn about. All I had to do was learn about C++ to do this. I learned very few browser things in order to port the C++ project to the web. It's not bad once you get there. Yeah.
I'm curious, when if we're not talking about porting existing software, but writing new for the web, web application.
Yeah.
What are some common use cases where I would benefit from doing it with WebAssembly instead of TypeScript or JavaScript?
Sure. Yeah.
Actual new application.
Totally.
Use cases that comes to mind.
Sure. Well, I mean, for me, one is like you just rather write in that language, and that's some of the Figma thing, right? Like the speed up that Figma gets is maybe 2x or something. I mean, it is possible to write very performant JavaScript. It just becomes very low level if you want to do the kinds of things that WebAssembly is doing. So you have to start being careful about doing things zero copy and using these array buffers. And like once you are doing that low level stuff, JavaScript is no longer the best language. Like, and maybe it never was, but I contend for some web stuff, JavaScript works pretty well. But once you start to care about performance, you can get there in JavaScript, but it is painful. And you can get maybe an extra 50% or something speed up by using WebAssembly versus the most possible optimized JavaScript. But the reason to do this is that it's much prettier code. It is much, if you're using something like Rust is the one I'm familiar with, but for new use cases. As you mentioned, I'm sorry, if I forgot to repeat the question, it was like, what are things, if you're doing new stuff, sure, if you're doing old stuff, of course you'd love to compile your old C++ program, your old C++ image compression algorithm to the web so you can upload files faster. But if it's new, why would you use WebAssembly? Is that fair? Yeah.
Yeah, I'm not questioning, yes.
Sure. Yeah. And so yeah, one of them is you're doing high performance things, and that's where people I've talked to are doing computer vision-ish thing or the self-driving car-ish stuff for visualizing the output from these things, like anything where you're doing it all in JavaScript, and then it starts to get real ugly because everything is linear, it's views on linear memory, and there are better programming languages for like reasoning about views on linear memory and giving it meaning and zero copy stuff. So that's one. But the other is the cross compatibility. JavaScript's almost everywhere. JavaScript, like, it's a great language. That's the one to learn, right? Like that's the thing that's taking over the world. But there are places where you can't run JavaScript, and you can run some binary that can be compiled to a lot of architectures. And if one of those architectures is WebAssembly, great, you can do WebAssembly there, and then you can still have a binary for other stuff. So that's the other big one, is I want this code to run in these multiple different places. And for me, there are other things like the plugin architecture. That's huge, right? Like Figma has a blog post talking about how this is a way you could do that. But if we're just talking about the browser and it's not an infrastructure question, then for me, I want to use that code somewhere else, or I'm trying to do low-level things that I'd really rather write in Rust or even C. Like it's just things that are easier to write in C when they have to do with using carefully reasoning about linear memory. Anything else?
All right. Well, ChatGPT has no more questions, so I think we can call it there. Thank you, everybody, for coming. Cool. Well, I want to thank Convex again for hosting the in-person part of this meetup. If anybody else anywhere in North America has any interest in hosting an in-person edition of this, we'd love to chat. You can get in touch with me or Matt or Tom or anybody who's associated with this, and we will happily set it up. If you are interested in talking either virtually or in person for the March edition of the meetup, again, get in touch with us, and we'd love to have more folks presenting. And with that, I think we'll call it a night. And thanks everybody for coming, live stream and in person. We appreciate it. Have a good night.
Great, thanks.